I Anand Jain from Hanumangarh, Rajasthan. Wish you a very happy New Year 2023. Today in our class 12th physics learning videos in our chapter electric circuit, we'll study balanced condition of Wheatstone bridge and solve some examination questions on balanced Wheatstone bridge. Let's start. This circuit in yellow highlight got 5 resistances P, Q, R, S and Z among 4 nodes A, B, C, D. Now none of these two have identical amount of current or identical amount of voltage. So P, Q, R, S, G are neither in series or nor in parallel to each other. So such circuit cannot be solved by series parallel simplification, and if we use Kirchhoff's law with 3 unknowns, the solution of such circuit need a tremendous effort and time. But a scientist, Wheatstone, obtained a special balanced condition of this circuit. In that balanced condition, the potential of B terminal and D terminal becomes identical. There won't be any potential difference between BD. So there won't be any current flow in this galvanometer branch, this mid section branch, and the current of P flows directly in Q and current of R directly flow in S. So this is just like flow of water in a river from P to Q, R to S without any water current across bridge. So this G section treated as bridge to river water flow or current flow, and such circuit is known as Wheatstone bridge circuit. And typical condition when this mid galvanometer section won't have any current flow is known as balanced Wheatstone bridge condition. When a voltage source is applied across A and C terminal of this Wheatstone bridge and current across BD section observed by this galvanometer by zero deflection as 0, then that particular condition is known as balanced condition of Wheatstone bridge. In balanced condition, the potential of point B and potential of point D become identical, and there is no potential difference across BD branch. So current in this section becomes 0. It means the potential drop across P from A to B and across R from A to D is the same, and let current in P resistance is X and current in R resistance is Y. Then voltage drop in P resistance is XP is equal to voltage drop in R resistance XP is equal to YR. This become our first condition, and in balance condition the total X current flows through Q and all the Y current will flow through S resistance. And again, since B and D got identical potential, C is a common point. So the potential drop across Q resistance between B and C and across S resistance between D and C is the same. That means XQ voltage drop of Q resistance is equal to YS voltage drop of S resistance. And if we simplify the two relation and obtain the ratio of current Y to current X, from first relation it is P divided by R, and from second relation it is Q divided by S. This relation of balanced can also be written as product of opposite resistance. P and S are equal as R and Q are opposite in this bridge. So P and S product is equal to Q and R product, and when such condition exists, there won't be any current flow through BD section. So this BD section can be treated as open circuited, and P and Q are taken as in series, R and S can be taken as in series, and this series combination of P and Q will become parallel to series combination of R and S. The same balance condition can also be treated as potential of B and D is same, so one can short circuit B and D, and in that condition resistance P and R resistance become in parallel, and similarly resistance Q and resistance S become parallel to each other, and these two parallel combination, one of P and R, second of Q and S, are in series to each other. So this circuit, which is earlier very difficult to analyze, become a convenient circuit for all sort of analysis if there exists a balance condition, and balance condition of Wheatstone bridge means the product of opposite side resistances are equal. That means product of P and S is equal to product of Q and R. In a Wheatstone bridge, a voltage source is applied across A and C, and galvanometer is placed across B and D to check balance condition, and when product of opposite side resistance P and S is equal to R and Q, then bridge is said to be balanced and there is no current in this galvanometer. And in this balance condition, if we interchange the position of galvanometer, which is right now between B and D terminal and voltage source, which is between A and C, and get a new circuit, then even in that new circuit where galvanometer is placed across A and C and voltage source is placed across B and D, the balance condition again prevails as the two resistance of opposite side, P and S product and R and Q product, is again the same. So in the balance condition of Wheatstone bridge, we can exchange the position of voltage source and galvanometer, and it will not change the condition of balance in Wheatstone circuit. In the circuit, 5 resistances are connected among 4 nodes, and we have to find out equivalent resistance across A and C terminal. Now in this configuration, no two resistance are in series or parallel to each other. So series parallel simplification of this circuit is not possible. So in such condition, we can check this circuit for balanced condition of Wheatstone bridge, as we have to find out equivalent resistance across A and C. So let's apply a battery with positive terminal at A and negative terminal at C. Now the other two terminal B and D could be current sensing galvanometer branch, and in balance condition there won't be any current in this 50 ohm section, provided the product of opposite side resistances, not adjacent but opposite. For 10 ohm, 20 ohm and 30 ohm are adjacent resistance, and this 60 ohm is opposite resistance. So the product of 10 with 60 and 20 ohm with 30 ohm is the same. That means this bridge circuit is balanced bridge, and in balance condition there won't be any current flow in this galvanometer section. So we can treat this galvanometer section as open circuit or equivalent to an infinite resistance, and when B and D section is open circuited across A and C terminal, current of 10 ohm directly passes through 30 ohm. So with single current flow path, 10 ohm and 30 ohm become in series equivalent to 40 ohm. Similarly, current of 20 ohm passes through 60 ohm, as there is no current in this galvanometer section, and 20 ohm and 60 ohm in series become equivalent to 80 ohm. Now 40 and 80 are in parallel to each other across A and C, and their equivalent resistance can be obtained by product by some relation, and it is 80 by 3 ohm. To find out resistance across A and C, we can analyze this circuit in a second manner, as this product of 10 and 60 and 20 and 30 is equal. That means this is a balanced Wheatstone bridge, and there is no current flow across galvanometer section, and potential of B and potential of D is identical. Identical potential points can be connected together, and when we connect B and D together, we short circuit this BD section, then we will find that this 10 ohm and this 20 ohm comes in parallel to each other. Similarly, 30 and 60 become parallel to each other. The parallel equivalent of 10 and 20 is 20 by 3 ohm, and 30 and 60 is 20 ohm, and these two resistances across A and C are in series to each other, and their series equivalent resistance as sum of individual resistance comes as the same, 80 by 3 ohm. So in balance condition of Wheatstone bridge, this mid section, we call it galvanometer section, can be either open circuited or short circuited, and the remaining circuit can be analyzed by simple series parallel analysis. In such circuits, when standard resistances are taken of constant material and connecting wire of copper are used, then copper and constant form a thermocouple junction, and when junctions are at two different temperatures, a small thermo EMF will be generated in copper constant thermocouple. Now to eliminate error of thermo EMF caused by temperature difference between junctions of two dissimilar copper and constant material contacts, we can take two readings by alteration of polarity of EMF source, and in one polarity if thermo EMF is supporting voltage source, in another polarity they may oppose EMF source action, and averaging of two reading will reduce the amount of error caused by thermocouple EMF of copper and constant. So in first case, the unknown R resistance is balanced by a standard resistance S1 value when the ratio resistance is P and Q, and in second case, when battery polarity is reversed, for the same resistance we got balance condition by new value of standard resistance S2, and as per balance condition the product of opposite resistance P and S2 is equal to Q and R, and new value of R could be written like this, and when we take average of these two readings, the error caused by thermocouple EMF get compensated. In bridge circuitry, when standard resistance is connected by connecting wires and contacts are made, there exists a certain resistance of connecting wire and resistance of contact. Now they may cause error in our measurement. And to eliminate such contact and connection wire resistance error, we take geometric average of two readings, with second reading obtained with change in ratio resistance. The ratio resistance P and Q are interchanged in second case. So in first case, P and S1 product is equal to Q and R product, and our R value is P S1 upon Q. And in the second case, when the ratio resistance P and Q are interchanged, the product of opposite resistance Q and S2, where S2 is new standard resistance value for balance, become equal to product of P and R, and our unknown resistance is obtained by this relation. And when we multiply the two, the ratio resistance get cancel out, and our R resistance would become geometric mean of two balance resistance S1 and S2 obtained by change of ratio resistance positions. This numerical will explain the previous theoretical concept. Now the balanced resistance is 8 ohm when ratio resistance P is across A and B and Q is across B and C for unknown resistance R. And when ratio resistance are interchanged, P is now placed across B and C and Q got its position across A and B. Then the same resistance is balanced by a new resistance value 4.5 ohm. So in both cases, the product of opposite resistance P and 8 is equal to Q and R. So R value is given by this formula. And in second case, when ratio resistance are exchanged, the product of opposite resistance Q and 4.5 is equal to P and R. So R unknown resistance is obtained in terms of ratio resistance as this expression, and when we make product of the two and square root, the ratio resistance will get cancel out, and our resistance value is square root of two balance resistance value S1 and S2. S1 is 8 ohm and in second case it is 4.5, and the product is 36 square rooted will give us answer 6 ohm. So this unknown resistance got a value 6 ohm. Now this reading is free from all contact or connecting wire resistance error. Wheatstone bridge circuit is very useful in several measurement and instrumentation schemes. One such application is called as meter bridge, which involve 1 meter long wire and two standard and unknown resistance can be compared by the balance condition of this Wheatstone bridge, and we can measure medium range resistance ranging from 1 ohm to 1 mega ohm by this method. A modified version of Wheatstone bridge got two ratio arms. Capital P and capital Q is one ratio arm and second is small p and small q. Such bridges are known as Kelvin double bridge, and they are used to measure small value of resistances which are less than 1 ohm, and during such measurement we can eliminate error caused by connection wire and contact resistance. Another modification of Wheatstone bridge is mega ohm bridge, which is used to measure high resistances of the order above 1 mega ohm. Interesting fact about Wheatstone bridge is that apart from measurement of unknown resistances, this bridge circuitry is also used to measure non-electrical quantities like faulty length of cables, temperature, force, weight, etc. While making measurement of unknown resistance by such Wheatstone bridge, the maximum sensitivity is obtained when the value of these two ratio resistance P and Q are of the same order, or unknown resistance and standard resistance are of the same order. In that condition, a small deviation in balance condition will produce maximum imbalance current in galvanometer, and we can make most sensitive measurement of unknown resistance. In our Wheatstone bridge circuits, these resistance wire is used in a coil configuration, and in coil configuration with resistance a little amount of inductance is also present, and during measurement we first connect voltage source to the circuit and allow a little time delay, then only we press galvanometer key so that transient current of coil inductance may settle and we'll get error free readings. In order to reduce the time delay in our measurement, we form resistance coils with negligible inductance, and to produce non-inductive resistance, the wire is first doubled and then a coil configuration of double wire is made for resistance wire, and in that case when current flow in the wire, two equal and opposite current will cancel each other's magnetic effect and we'll get a resistance without any inductive effect, non-inductive resistance by such configuration. Many a time we have to analyze a circuit which looks very complicated. Here this complicated circuit is supplied with V volt and we have to find out current in all these resistances, and the circuit clearly shows that no two resistance are in series or in parallel to any other, so we cannot apply series parallel simplification. So one has to doubt about such circuits being a balanced Wheatstone bridge, and in such circuits, apart from two battery connection, there are two other nodes as this C and D, and if there exists a Wheatstone bridge, then it may be balanced, and in that balance condition check, just remove this galvanometer section resistance and check the product of opposite resistances, this resistance and this resistance, and this resistance with this resistance, and definitely for a balanced Wheatstone bridge the product of opposite resistance would be the same, and in that case we can open circuit this section and current in DC branch or in this resistance will become 0, and the remaining circuit, this R and this R, this R and this R become in series 2R. Similarly, this R and that R become 2R, and now in this resistance R directly V voltage applied, its current is V by R. In these two resistances, in this case current is V by 2R, and similarly here also current is V by 2R. Here 5 different resistances are connected to 18 volt source in this complex configuration, and we have to find out current in all resistances. Since we cannot apply series parallel simplification, so it might be a balanced Wheatstone bridge, and in this circuit there is a resistance which is not connected to any one of the two terminal of voltage source, and that resistance is this 5 ohm. It would be that galvanometer branch which in case of balanced Wheatstone bridge won't have any current, and it can be open circuited. Now the remaining circuit, whether a balanced Wheatstone bridge or not, can be checked by check of product of opposite resistances 4 ohm and 3 ohm and 6 ohm and 2 ohm, and since the two product are same, so it is confirmed that this part of circuit is a balanced Wheatstone bridge that won't have any current in galvanometer section. So this 5 ohm can be open circuited, and its current is also without any calculation can be obtained as 0. Now after open circuiting galvanometer section, this 4 and 2 ohm are in series, and this 6 ohm across 18 volt would have 3 ampere current. So current of 4 ohm and 2 ohm is 3 ampere. Similarly, this 6 ohm and 3 ohm are in series, and across this series combination of 9 ohm 18 volt will produce 2 ampere current. So current of 6 ohm and 3 ohm is 2 ampere. So we have obtained current of all resistances, as this is a balanced Wheatstone bridge. We have to find out equivalent resistance across these two terminal A and B in this complicated electric circuit. Now this circuit is symmetrical circuit. About this line passing through O and perpendicular to AB, the part here and part here are identical. That means this O point is mid potential point for A and B. That means voltage drop in AO section by current flow and voltage drop in OB section by current flow is the same, since the two resistance are same. So these two currents are also same. So we can say current of AOB section won't go through this 3 ohm or that 3 ohm, or current from these two 3 ohm won't pass to AOB section. So we can isolate this connection as shown in this diagram, and when this isolation is done, these two 3 ohm are in series become 6 ohm, and 6 ohm in parallel to 3 ohm become equivalent to 2 ohm. Now that 2 ohm and 3 ohm and 3 ohm are in series become 8 ohm, and that 8 ohm is in parallel to 6 ohm. So 8 and 6 parallel got an equivalent resistance 24 by 7 ohm for this circuit across A and B. So in last 20 minutes we have explained each and every part of balanced Wheatstone bridge. We have explained condition of balance, and we have also explained all practical considerations of our measurement. We have also solved good number of numericals based on balanced condition of Wheatstone bridge, so that during examination you can solve similar type of questions with great ease. Our other learning video of class 12th physics are equally useful in examination preparation. You can use them in your studies and can share the same to your friends. If you want doubt clearing session on our online classes with useful study notes, do join YouTube membership of our channel by pressing join button just beneath. Happy learning. Thank you very much.